Jai Hind everyone. Myself Dr. Sharma from Ajay Kumar Garg Engineering College, Ghaziabad. The subject which I am taking, name of the subject is Engineering Physics and the subject code is KAS 101T. The topic which I have started, name of the topic is Relativistic Mechanics. And we have already discussed that in order to describe the motion of any object, we always require a frame of reference. So we have already discussed that there is a set of 4 coordinate axes, basically 3 space coordinates, that is x, y and z, and a time coordinate, that is t, and this particular set, this is used to describe the motion of any object. Then we have discussed about classical mechanics and relativistic mechanics. Classical mechanics, which is also known as Newtonian Mechanics, and in classical mechanics we are dealing with moving objects, but the speed of those moving objects is very small with respect to c. Whereas in case of relativistic mechanics, we are dealing with those moving objects which are having a speed very large, comparable to c, means that v is comparable to c in case of relativistic mechanics. But that relativistic mechanics is equally applicable at low speed. So that is the main difference. Means in classical mechanics, you can describe the motion of only those objects which are moving with a very low speed with respect to c. Whereas in relativistic mechanics, you can describe the motion of moving objects which are moving with a higher speed. Higher means that speed is comparable to c, as well as you can describe the motion of those objects which are moving with low speed, means it is equally applicable at higher as well as a lower speed. So in other words, you can say that classical mechanics or Newtonian mechanics, that is a special case of relativistic mechanics. And the main difference between classical and relativistic mechanics is, in classical mechanics everything is absolute, means the length, mass, time, all these parameters, they are not affected by the motion. Whereas in case of relativistic mechanics, nothing is absolute, everything is relative. The motion of an object, that is going to affect all the parameters associated with the moving object. So we have discussed about inertial and non-inertial frames. Inertial frames, which are also known as unaccelerated frames, and non-inertial frames, which are accelerated frames. So we have discussed about them. After that, we have discussed about Galilean transformation equations. Then using those equations, we have derived velocity transformation and then acceleration transformation. And today we are going to start with this ether hypothesis and Michaelson-Morley experiment. Right? So in the last lecture, we have already discussed about this ether hypothesis. So what is this ether hypothesis? It was assumed that for the propagation of all type of electromagnetic waves or sound waves or water wave, a medium is always required. So it was assumed that universe is filled with a hypothetical medium, and that medium is known as ether. This medium is perfectly non-resistive, having high elasticity, negligible density, and all objects of universe, lighter as well as heavier, they are moving freely in this medium. So it was assumed that this particular medium, this will act as a rest frame. It will act as an absolute frame. Why I am saying it will act as an absolute frame? Because you can describe the motion of any object of this universe with respect to ether. So that is a reason this ether is known as absolute frame of reference or rest frame of reference, or one more name is there, it is known as zero frame of reference. Right? So many experiments were performed in order to prove the existence of ether medium, and the most famous experiment is Michaelson-Morley experiment. So today I am going to discuss that Michaelson-Morley experiment here. So basically Michaelson and Morley, they performed this experiment at the beginning of 19th century to prove the existence of ether medium, right? So Michaelson-Morley experiment, Michaelson-Morley, they performed an experiment to prove the existence of ether by finding relative velocity of earth with respect to ether. So what assumption they have taken? According to Michaelson-Morley, since Earth is also part of our universe and Earth can also move freely in ether medium. So if this is the case, then they have assumed that since there is a medium like ether medium and Earth is moving freely in that medium, it means we can find the relative velocity of Earth with respect to ether. So if you are able to find the relative velocity of Earth with respect to ether, then the straight way we are having this conclusion that there is a medium like ether medium. So the objective of this experiment was to prove the existence of ether medium by finding the relative velocity of Earth with respect to ether. So that was the objective. Now you know whenever you will perform an experiment, then you should know what is the objective. So objective is clear to you. Objective is to find the relative velocity of Earth with respect to ether. And by finding that relative velocity of Earth with respect to ether, they tried to prove the existence of ether medium or ether frame. Now the next point is, in any experiment, you should know what is the experimental setup with the help of which you will perform that experiment. So now I am going to describe the experimental setup here. So now the experimental setup is like this. First we have a source of light. So there is a monochromatic source of light S. Then there is a beam splitter. Beam splitter means when light will incident over it, it will divide the light into two parts. So you have a monochromatic source of light and then you have a glass plate which is semi-silvered. Semi-silvered means some part of the light that will pass through that plate and some will be reflected. So that will act as a beam splitter there. So what is a beam splitter here? That is a semi-silvered glass plate, right? This glass plate that will split the light into two coherent rays. Why I'm saying that you are going to get two coherent rays? If you are having two independent sources, then you can never get coherent light. So the method to get coherent light is either you can divide the wavefront of light. By division of wavefront you can get coherent light, and the second method is you can divide the amplitude of a single ray into two parts. If a single ray is divided into two parts, then those two rays will be coherent in nature. Why I am saying that those rays will be coherent in nature? Because they are obtained from a single source. They are obtained from a single ray. If there will be any change in the phase of that parent source or parent ray, you will get the similar type of changes for both the rays which are splitted through that beam splitter. That is the reason those rays are known as coherent rays. So the plate which is semi-silvered, which is acting as a beam splitter here, that plate will divide the light into two coherent rays, right? One will be reflected and one will be transmitted. Now in this experimental setup, there will be two mirrors. One mirror, suppose the position of one mirror is this, then the second will be just perpendicular to this. If this is your first mirror, then second mirror is at this particular position. So one ray will move toward this direction and the other will move toward the second mirror. And the front surfaces of those mirrors, they are highly reflecting. Clear? So again I am repeating this. Objective of this experiment is to prove the existence of ether medium by finding the relative velocity of Earth with respect to ether. If you can find the relative velocity of Earth with respect to ether, you can say there is a medium like ether medium. Second one, now we are describing the experimental setup here. So basically the name of setup which is used to describe this experiment, that name is Michaelson interferometer. And when I am saying interferometer, it means it is based upon the phenomena of interference. And you know, in order to get interference pattern, there should be coherent rays and they will superimpose, then you will get an interference pattern. So how you are getting that? In this experimental setup, first you have a monochromatic source of light. Then you have a beam splitter. And what is a beam splitter here? Beam splitter is a glass plate which is semi-silvered. So when light will incident over that glass plate, some part will be reflected, some will be transmitted. So those two rays, that is reflected and transmitted, those rays will act as coherent rays. Why I am saying those will act as coherent rays? Because they are obtained from a same ray, same source, so they are coherent in nature. After that next part of that Michaelson interferometer is two mirrors with their front surfaces highly silvered, and those two are perpendicular to each other. So this is the experimental setup. As you can see here, this is your monochromatic source of light. This particular source is having a fixed wavelength. Let lambda is the wavelength of this particular source. Now this is your glass plate. This one, this blue color, this one is glass plate, and this glass plate, it is inclined at an angle of 45 degree to the direction of incidence of light. This is the direction of incidence of light, and this light ray will strike over this glass plate, and this glass plate is making an angle of 45 degree with the direction of incidence of light. Then you are having two mirrors here. This is your M1 and this one is M2. Front surfaces of these two mirrors, they are highly reflecting. Means when the light will strike over the front surface of M1 or M2, light will get reflect back and it will follow the same path and it will come back to this plate. Let the name of this plate is capital P. Let this glass plate is P. This glass plate is semi-silvered, so it will act as a beam splitter here. It will divide the light into two parts. Some part will be transmitted, that transmitted part will move towards M1. Some part will be reflected, that part will move towards this mirror M2. So this is your experimental setup, and one more component is there, that is your telescope. This is your telescope, and the role of this telescope is to observe that interference pattern. This is Michaelson interferometer, and through this you are going to observe the phenomena of interference here. And if you are getting an interference pattern, that interference pattern will be observed through this telescope. So again I am repeating this experimental setup. The first component is this monochromatic source of light. Second one, this semi-silver glass plate, which will act as a beam splitter here. Why it is beam splitter? Because it is going to divide a single ray into two parts. One is transmitted and one is reflected. So these two rays, there is a division of amplitude. So these two rays, since they are generated from a single ray, these two will act as coherent rays, right? M1 and M2, these two mirrors are there. And you have to remember that M1 and M2, they are held perpendicular to each other. If this is the position of M1, then this is the position of M2. They are held perpendicular to each other. And one more point, this distance PM2, if this is L, then this PM1, this is also L. Means both the mirrors, they are kept at an equal distance from this glass plate P. And a telescope T is there, which is going to observe the interference pattern. So this is our experimental setup, and now we are going to describe the working process here. So in order to describe that working process, what you have, from this monochromatic source of light, light will incident over the glass plate. So when the light will incident over the glass plate, light will divide into two parts. Transmitter will move towards M1, reflected will move towards M2. And you know what is this PM1? This is your L. And what is this distance PM2? It is your L. Means this optical path is L, this one is also L. So when this light ray, which is transmitted by this glass plate, when it will start its journey towards M1, then it will travel an optical path L. Light will reach over the glass plate, over this mirror M1, and its front surface is highly reflecting. So light will be reflected back by this mirror M1, and again it will follow the same path and it will reach over this glass plate. It means during this forward journey, the light will travel an optical path L, and during the backward journey, again the light will travel an optical path L. That is for your transmitted ray. Now the reflected ray, that will start its journey from glass plate towards the mirror M2. Front surface of mirror M2, that is highly reflecting. So when light will strike over this, it will be reflected back and it will follow the same path. So during the forward journey, light will travel a distance L. During the backward journey, again light is traveling a distance L. So this for transmitted ray and this one for reflected ray, right? The separation between P and M1 and P and M2 is same and is equal to L. It is mentioned over here and I have already discussed with the help of this. And this separation is called length of the arm. The light will reflect it back from the mirrors M1 and M2, that I have already mentioned here, that these front surfaces are highly reflecting. So light will be reflected by M1 as well as M2 and light will reach over this glass plate. Now you have light, both the light rays over this glass plate P. Now these two, they are coherent in nature. Why I am saying these two rays are coherent in nature? Reason is that they are obtained from same ray, and these two, they will be directed toward this telescope. So this particular ray, which is reflected ray, and this one transmitted ray, both will reach over the glass plate and then they are directed towards this telescope. So when these two rays, they are moving towards this telescope, both are coherent in nature, both will superimpose. So when both the rays will superimpose, then at certain points the intensity will increase as compared to sum of individual intensities. That those points will be points of maxima, and there will be certain points at which the two rays will superimpose in such a way that their intensity is less than the sum of individual intensities. So those points will be points of minimas. So what I mean to say, that when these two rays will superimpose, you will get an interference pattern, and that interference pattern is observed through this telescope T. So this is a working process. What is a working process? From the monochromatic source of light, light will incident over the glass plate, which is beam splitter here, which is semi-silvered here. Some part will be reflected will move towards M2. Some part will be transmitted, that will move towards M1, right? Since both the mirrors, they are kept at an equal distance from glass plate P. So this distance is L, this one is also L, right? And front surfaces of both the mirrors, that is highly reflecting. So both the rays, when they will reach over the mirrors, they will be reflected by the mirror and they will come back to glass plate P. Then those two rays, that is reflected and transmitted, they are directed towards the telescope, and when they are directed towards the telescope, they will superimpose and you will get an interference pattern, right? So this experiment was performed by Michaelson and Morley in 3 steps. First step, when this apparatus is at rest. So this is your case number 1. It was assumed that this apparatus is at complete rest. If I am saying that apparatus is at absolute rest, it means this apparatus is somewhere present in ether frame. So your case number 1, when apparatus is at rest, absolute rest, it means your apparatus is in ether medium or ether frame. So when apparatus is in ether frame, then what will be the time taken by this transmitted ray to move from glass plate to M1? Now tell me, what will be the time to travel this journey from P to M1? What is the path? Path is L. And since light is traveling this path, that will travel that path with speed c. So the time taken to move from P to M1, that time taken will be L by c. Light will be reflected by the front surface of mirror M1. It will reflect back and again it will travel an optical path L with same speed c. So what will be the time taken? That will be L by c. It means if we are talking about the round trip means the time taken by the ray to move from P to M1 and then from M1 to P. So that time taken will be for forward journey L by c and for the backward journey again L by c. So what is the time taken? The time taken is 2L by c. So the time taken by this particular ray to move from glass plate to mirror and then from mirror to glass plate is simply equal to 2L by c. Where what is L? That is the distance between glass plate and mirror. or you can say that is your length of the arm, right? Now for the transmitted ray, for the reflected ray, for this particular portion, the time taken by the light to move from P to M2, what is this distance? L. Light is traveling this distance, it will travel with speed c. So what is the time taken? Time taken for the forward journey, that is L by c. Time taken for the backward journey, when reflected by front surface of mirror M2, it will come back, and when it is coming back, again it will follow, it will cover a distance L with speed c. It means that T2 is the time for the transmitted ray. For the forward journey it is L by c, and for the backward journey again it is L by c. So what is the total time taken? It is 2L by c. So what conclusion you are drawing from this particular discussion? Conclusion is the time taken by the reflected and transmitted ray to cover the round trip. Round trip means P to M1 and then from M1 to P, P to M2 and then from M2 to P. That time taken by the by reflected and transmitted ray to cover the round trip is 2L by c when apparatus is assumed to be at rest. So this is your case number 1. Means your T1, that is simply 2L by c. What is T1? Time taken by that transmitted ray to travel that optical path. And your T2, that is also equal to 2L by c, right? So what is the time difference? If you want to find the time difference between these two, then time difference is 0. Means both the rays, reflected as well as transmitted, they are taking same time, they are taking equal time to move from glass plate to mirror and then from mirror to glass plate. It means after this complete trip, after this round trip, they are reaching over the glass plate at same time. So that time difference is 0. And then these two, that time difference is 0, these two are directed towards the telescope, then they will superimpose and you will get an interference pattern. So that interference pattern, when apparatus is at absolute rest, that is known as your reference interference pattern, right? This is the if that is a reference interference pattern, means that is the position of interference pattern when this apparatus was assumed to be at rest or in ether frame. Now with respect to this reference position, we want to find the shift in the interference pattern when this apparatus is somewhere at the surface of Earth. So if there is any relative motion between Earth and ether, you will find a change in the position of that interference pattern. And if there is no medium like ether medium, then you will not find any change in a position of the interference pattern. So this was your case number 1. I hope case number 1 is clear. So in Michaelson model experiment, what is the objective? Objective was to find the prove the existence of ether by finding relative velocity of Earth with respect to ether. Then you have apparatus, experimental setup. So the apparatus which you are using, that name of the apparatus is Michaelson interferometer. And what are the main components of that interferometer? Your source of light, monochromatic source of light. Your beam splitter, which is a glass plate inclined at an angle of 45 degree to the direction of incidence of light. Then you have two mirrors, M1 and M2, with their front surfaces highly reflecting, and both are kept at an equal distance from the glass plate, and a telescope T. This is your experimental setup. Name is Michaelson interferometer. Why the name interferometer is given? Because it is based upon phenomena of interference. And where are your coherent rays? These rays, when they are divided by this beam splitter, your transmitted as well as reflected ray, since both are obtained from a same ray by the division of amplitude, so you can maintain a constant phase difference. So that is the reason those two rays are known as coherent in nature. So we are taking case number 1 when apparatus is assumed to be at rest. So at rest, or you can say when apparatus is is in ether frame, in that case both the rays, that is your transmitted as well as reflected, they are taking same time to cover this round trip from glass plate to mirror and then from mirror to glass plate, from glass plate to mirror and then from mirror to glass plate. Time is 2L by c, 2L by c, time difference is 0. Then both the rays, coherent rays, they are directed towards the telescope, they will get superimposed and you will get an interference pattern, right? This is your case number 1. Now we will discuss case number 2. So in case number 2, what we have here, in case number 2, now the apparatus is kept somewhere at the surface of earth. In case number 1, it was assumed that apparatus is at absolute rest. Now this apparatus is kept somewhere at the surface of earth. So when it is somewhere at the surface of earth, it is moving with the velocity of earth, means the velocity with which apparatus is moving, let apparatus is moving along this direction with this constant velocity with respect to an observer who is sitting in absolute frame. What is your absolute frame? Your ether frame. Means your observer is sitting in ether frame, but your apparatus is at the surface of earth. So when apparatus is at the surface of earth, then for the observer who is in ether frame, that apparatus is moving. So this apparatus, suppose the direction of motion of the apparatus is along this transmitted ray. Suppose your apparatus is moving along the direction of your transmitted ray. So that is your case number 2. Now again the working process is same. Working process means the light will strike over the glass plate, then it will divide into 2 parts, that is your reflected and transmitted. Then they will reach over the mirror M1 and M2, they will be reflected by those mirrors and then they will come back to the glass plate, then they are directed towards the telescope, then they will get superimposed and you will get an interference pattern. Now we will try to find out that if apparatus is moving with this much velocity, then what is the change in interference pattern? What is the change in the time which is taken by the light rays for covering that round trip from glass plate to mirror and then from mirror to glass plate? We have to find that change. Clear? So for that, again you have same apparatus. This is your monochromatic source of light S. From this source, light will incident over the glass plate. So when light will incident over the glass plate, it will divide into 2 parts because this glass plate is acting as a beam splitter. One part, that is a transmitted part, that will move toward this particular mirror, and the reflected part that will move toward this particular mirror. These rays, they will reach over the mirror M1 and M2. This is your M1 and this one is M2. Please refer your first diagram of Michaelson model experiment. Then they are reflected by the front surfaces. They will come back to glass plate. This ray will also reflected by the front surface of mirror M2 and it will come back to glass plate P. So then those coherent rays which will reach over the glass plate, they are directed towards the telescope and then they will get superimposed and you will get an interference pattern. So now what is a change? That change you will try to find out here. So when light will reach over the glass plate, this will be your reflected part. Now the reflected ray, let that ray is taking time. First we will discuss this transmitted ray here. So we are starting with the transmitted ray, then we will come back to reflected. So if you are able to understand this diagram here and geometrically if you are able to find out the value of all those paths or distances, then it is very easy to understand. So the transmitted ray that is moving toward this direction during forward journey, the transmitted ray is moving along this direction. Now if I am observer who is sitting in ether frame, then for me this entire apparatus, it is moving along this direction with this particular speed and your apparatus is also moving, right? Your apparatus is moving with this speed and the light ray that is also moving with speed of light. It means this light ray, when it is moving toward this direction, then for observer who is sitting in frame, ether frame, for that observer the speed of light is not c. Because of the speed of this apparatus during the forward and backward journey, the speed of light will be different. So as the apparatus and light both are moving in same direction, that is when light is moving towards m2, this is your m2, thus the relative velocity will be c minus v. So for this forward journey, the speed of light will be c minus v, and when it is reflected and it will come back, then the speed of light will be c plus v. Initially when apparatus was at rest, this v was equal to 0. It means both the rays this ray when moving toward this direction, it was traveling with c, and when the ray was moving in backward direction, it was traveling with c. But now it is not traveling with c, it is traveling for the forward journey with c minus v, it is traveling with c plus v for the backward journey. So what is the time? What will be the time taken? You know the time taken will be equal to, it will be L upon c minus v, and for the other one it will be L upon c plus v. So if you will solve it, then you will get here, it is 2L c upon c square minus v square. So there is a change initial, and if you will take c square common, then that c square and the c will get cancelled, and you will get here 2L by c upon 1 minus v square upon c square. What was the time taken when the apparatus was at rest? In case number 1, when apparatus was at rest, what was the time taken? That was simply 2L by c. But now the time is different. It is 2L by c upon 1 minus v square upon c square. And why you are getting that change? You are getting that change because of the speed of this apparatus with respect to an observer who is sitting in ether frame. So your T1 dash is equal to this. So this is for transmitted ray. Now we will discuss the time taken by the reflected ray to move from glass plate to mirror. This is your mirror M1, and then from mirror to glass plate. For this ray, we will find the time taken, right? So in order to find that, what we are going to do here, suppose your light ray, when reflected by this glass plate, it is starting its journey and it is moving towards mirror M1. So when this light ray that will reach over the mirror M1, let the time taken by this light ray, let that time taken is t dash. So if in time t dash, light is moving from glass plate to mirror, but you are sitting in, you are observer, you are sitting in ether frame, and for you this apparatus is moving, and if this light ray is taking t dash time to reach over the mirror, then during t dash time, since apparatus is moving with this much speed, this mirror will occupy a new position. That mirror will not be present at the same point. There is a new position for this mirror in time t dash, So if light is taking time t dash to move from glass plate to mirror, then during that time, this mirror will occupy a new position, and let that M1 dash is the new position of the mirror, right? So can you tell me what will be the displacement M1 dash? This position is occupied in time t dash with this speed. So this displacement M1 dash, that will be your Vt dash, because in t dash time this new position is occupied by the mirror and with speed v, so that displacement is Vt dash. So it means now the light ray that will move from glass plate and it will reach over the mirror M1, and this distance is travelled in time t dash. So if distance is travelled in time t dash, and this will be then Ct dash, because light is travelling this distance and travelling in time t dash, so this is Ct dash. Now you are getting a right angle triangle here. This glass plate, let the position is P, this one is M1, this one is M1 dash. So you have a right angle triangle P M1 dash. You know this side is Ct dash, you know this one is L, and you know this one is Vt dash. So if you have this right angle triangle here, where let this is P, let this is M1 and this is M1 dash. This is your CT dash, this one is your VT dash and this one is your L. So according to Pythagoras theorem, for this right angle triangle, you can write C square T dash square is equal to L square plus V square T dash square. You have to just simplify it, and after simplifying we will find the value of T dash, and if you will simplify it, your T dash is L by C upon under root 1 minus V square upon C square. Just simplify it and find the value of T dash. So according to the simple theory of optics, when this light ray it is starting its journey from glass plate towards the mirror M1, and if it is taking time T dash to move from glass plate to mirror, then during that time mirror will occupy a new position, and since that position is occupied in time T dash with the speed V, so this displacement is Vt dash. This length or optical path, that is CT dash, and this you know already, it is L. So now you are having this right angle triangle, and using Pythagoras theorem, from this right angle triangle we can find the value of T dash. So your T dash is equal to this. So T dash is the time for journey, for the forward journey, means from glass plate to mirror M1. But over the front surface of mirror, light will be reflected by that mirror, and then it will come back to glass plate. So the light ray will take same time to move from glass plate to mirror. It means the total time taken, that will be T dash. It will be twice of, that will be T2 dash, and it will be twice of T dash. So what is the time now? It is your 2L by C and divided by root of 1 minus V square upon C square. So what was the value of T2 when apparatus was at rest? That was simply 2L by C. What was the value of T1 there? That was 2L by C, means T1 and T2 both were equal there. But now you can see T1 and T2 both are different. One is 2L by C upon 1 minus V square upon C, and the second one is 2L by C upon under root 1 minus V square upon C square. What is the meaning of this? The meaning of this is, these two rays, they are not taking same time. This ray transmitted and this reflected ray, they are not taking same time to travel this journey, to travel this path. They are taking different time. This transmitted ray, that is taking time 2L by C upon 1 minus V square upon C square. This is the time taken by transmitted ray, and the time taken by the reflected ray, that time is simply 2L by C upon under root 1 minus V square upon C square. So now you can see there is a difference in time, means both the rays, they will reach over the glass plate at different times. So if the light rays, they are taking different times, then there will be a time difference. What was the time difference when apparatus was at rest? Time difference was 0, but now that time difference is not 0. It is having some different value, right? So we have already done this particular part. Your T1 is 2L by C into 1 minus V square upon C square here. So 2L by C is equal to this. And your T2, that is equal to 2L by C upon under root 1 minus V square upon C square. A difference in these two. What is done over here? Just simplify it using binomial expansion. So your T1 is 2L by C into 1 plus V square upon C square. Just simplify this. This is for transmitted ray. This is for transmitted part. You know what is the value for transmitted part. This is for transmitted and this is for reflected. So that is a difference. Now just using binomial expansion, find the value of T1 and T2. So your T1 is equal to this using binomial expansion and neglecting the higher terms. Why you are neglecting the higher terms? Because in the higher terms you are having c raised to power 4, c raised to power 6 in the denominator, and that power will be denominator will be very, very large with respect to that denominator is large, so the entire term that will give you very small value with respect to 1. So with respect to 1 you can neglect the higher terms, and your T2 that is equal to this particular value. And this is a time for reflected ray, this is the time for transmitted ray, right? And the time difference delta T, this is equal to, the time difference in this particular case is equal to 2L by C 1 plus V square upon 2C square, this reflected time for reflected time minus the time of reflected ray. So finally you are getting this is a time difference. The time difference between the two rays, that is equal to LV square upon C cube. From equation number 3, you can derive a very important conclusion. If V is equal to 0, what will be the time difference? If V is equal to 0, then the time difference is equal to 0. It means this time difference will be there only because of this velocity of apparatus with respect to ether frame. So only because of this particular term you are getting a time difference. If there is a time difference, then there will be a path difference. So yes, this is time difference, and after finding this time difference you can find a path difference. This is your case number 2 of Michaelson model experiment. In case number 1, apparatus is at rest. In case number 2, apparatus is moving, and that is moving with respect to an observer sitting in ether frame. So you are getting a time difference here, means both the rays, they will reach over the glass plate at different times. So if both the rays are reaching over the glass plate at different times, so there will be a time difference, there will be a path difference. Now these two, they are directed towards this telescope. So these two rays will superimpose because they are coherent in nature. When they will get superimposed, you will get an interference pattern. But the position of that interference pattern, that will be different as compared to the interference pattern of case number 1. Why there is a difference? Because in case number 1, time difference was 0, path difference was 0. But in case number 2, there is a time difference, there is a path difference. So there will be a shift in the interference pattern. We will find that shift. So in next lecture, we will try to find out that shift in the fringes. And using that shift, we will try to verify the existence of ether frame. Thank you for today.